there's one more thing I want to do, and that's come back to the fact that I told you before, but now that we can actually make more explicit. And that fact was when we were talking about currents and integrating out off-shell particles, we saw that you start with these guys, you start attaching them, and you end up with a Wilson line. I'd now like to make it obvious that that kind of manipulation always is true, that we can always get rid of this field and put it in terms of a Wilson line. And the notations that we've introduced are going to allow us to do that. So let's have a little aside on that fact. So if you are in momentum space, the Wilson line has an equation of motion, or a defining equation if you like. It's this. This defines the direction that the Wilson line is along the n bar direction. And the x and the minus infinity are telling you what the endpoints are. So this is the defining equation. You can look back at Peskin if you want to see how that all works. And that's the defining equation in position space. But we've just advocated for a kind of momentum space notation. So what's the corresponding equation in momentum space? It's pretty simple. If we go over to our momentum space Wilson line, we just go over to our momentum space covariant derivative, and the defining equation is this. OK, so the notation in some sense is pretty simple. We just have to switch objects. If we write out what that derivative is, then it's that. OK? So now consider the following thing. Consider this combination. But let me think about it as an operator equation. So let me think about it as if there could be something to the right. If there's something to the right, then the p bar can act on that thing too. So I get 0 if the p bar acts on this thing, but if the p bar acts through, then I get just p bar on the operator. So as an operator equation, I can erase the O. This is true for any O. And we have this operator equation. But I know something else. I know that the Wilson line is an e to the I something, and actually it's unitary. So W dagger W is 1. And again, in momentum space notation, that's kind of the obvious thing. W dagger W is 1. And that means I can multiply this equation here on the left or the right by W daggers. And so if I do that, let me multiply by W dagger. Then I can write I n bar dot dn is Wn p bar Wn dagger. So the gauge field G n bar dot an, because of gauge symmetry, it's always going to show up in the covariant derivative. So it's always going to show up in this combination. And this equation is telling me I can switch that for Wilson lines in this p bar if I want to. I could have also multiplied things the other way around and written that p bar, so sort of by way of completeness, I could have written that as well. It's also easy to convince yourself of the following. 1 over p bar is Wn dagger 1 over Im bar dot d w, and 1 over Im bar dot d. I'll check that I got the daggers in the right place. But these two equations are true, which are kind of the inverse of those equations. So how do we check that? Well, just multiply this times this, you should get 1. Right? And if I multiply, say, on the right here, then the W dagger here kills the W dagger, and the P bar kills the P bar, and then the W kills the W dagger. So those are true. And so we can put this into the Lagrangian if we want. And we can do what I said, that we can actually, if we want to, get rid of the m bar dot a field for the collinears, write it in terms of Wilson lines. And we'll use this from time to time when it's convenient. If we used it in the Lagrangian becomes this thing. So that 1 over Im bar dot d becomes this thing. And in some sense, you might think that this is easier to expand if you know the expansion of the Wilson line. Then you just have to let a 1 over p bar act on this full combination of fields. And it just gives the total m bar dot p momentum of that full combination of fields. OK, so that's kind of this. I claimed this was true, and now I show you in a kind of non-trivial case how with these operator manipulations we could just quickly go back and forth, and it's related to the fact that it appears in this combination. We'll talk more about gauge symmetry later on. I'm alluding to it from time to time, but we'll talk about it more precisely later on. We have to do this story for the collinear Gluon Lagrangian. And much of this is just repeating what we've said for the quarks, for the gluons. And once we know how to write down the covariant derivatives, then it's actually not so complicated. And there's just one little complication that we should be careful about, which I want to emphasize to you. And so we'll go through it. Let me write the Lagrangian in QCD in terms of traces. And let me use a general covariant gauge. So this is a general covariant gauge fixing term, which we call the gauge parameter tau. And then we have some ghost fields as well. And of course, G mu nu is the usual G mu nu A T A. And that's my sign convention, commutator of two derivatives with the I over G. So we do the same steps to get SET. And so really, do we just have to take, if you think about writing all the G's in terms of D's, we already know how to split the D's in terms of ultrasoft and collinear parts. And so that's what we do. So let me write out a D, which is kind of a leading order D, and we'll just set up some notation, and then I can just basically write down the answer. So let's set up a curly D that has all the sort of pieces that will survive at leading order. So all the pieces that survived were the collinear pieces in perp and in bar, and then in the n direction, both pieces. And effectively, I'm just changing all the regular Roman Ds in my gluon action into these curly Ds, and that's almost the entire story. And the one place that it's not so, So from a kind of power counting perspective, once you take into account that when you dot things, right, n's are always dotting within bars, so it's this times this, so this is lambda squared, this is order lambda 0, this guy dots into himself, so you get lambda squared there as well. So for power counting purposes, when you start squaring things, they're all going to be homogeneous with this setup. So basically, that's what I'm saying here. And then there's one complication, and that's this partial derivative. Well, there's two partial derivatives. There's one there, and there's one there. So this is in the gauge fixing terms. These terms are both related to the gauge fixing. And in those terms, actually, I want to make them covariant. So let me define one more thing. I want to make them covariant, but I want to make them only covariant under the ultrasoft part of the action. So here's just pulling out the pieces that would have the ultrasoft field and making a derivative that I'll call curly d ultrasoft. So one way of thinking about that is that it would be like background field gauge. In background field gauge, you'd make this partial mu into the d mu of the background, involving the background field, and that would be background field gauge. So from the point of view of the ultrasoft field, being a background field, it's very natural to have a replacement that looks like this. And that's one way of arguing. Really what's going on in the effective theory is that this is general covariant gauge for AN. That's what we want it to be for AN mu. This should be the gauge fixing term for the collinear gluons, and it shouldn't be breaking any gauge symmetry of ultrasoft gluons. So we'd actually like the Lagrangian to both have gauge symmetry for collinear gluons and a separate gauge symmetry for the ultrasoft gluons. Since this guy is supposed to be gauge fixing for the collinear gluons, we don't want it to be doing anything to the ultrasoft gluons. And that's accomplished if we make this replacement that I partial goes to I curly d. All right, so we could write out what LCG0 is, but it's just these two replacements. Since we're out of time, I'll just say that. And sort of write out the fields in the notation that we developed.